Good morning to all. Myself Sanjana K, student of structural engineering and construction management. My topic is design considerations of retaining wall. First one, retaining wall design and proportioning. Firstly, the approximate dimensions are chosen for the retaining wall. Stability of this wall is checked with these dimensions. Section is changed if it is undesirable from the stability or economy point of view. This is the figure. This is the approximate values are given for the retaining wall. Next one, force on the retaining wall. The main force that acts on a retaining wall is pressure due to retained material. The earth pressure tries to overturn and slide a retaining wall. The magnitude and direction of the earth pressure can be determined by applying the principles of soil mechanics. The pressure exerted by the retained material is proportional to its density and to the distance below the earth's surface. Typical plane of rupture behind a retaining wall is shown in figure. Next one, design considerations. In order to calculate the pressure exerted at any point on the wall, the following must be taken in account: height of water table, nature and type of soil, subsoil water movements, type of wall, material used in the construction of wall. The following two forms of earth pressure need to be considered during the process of designing a retaining wall. First one is active earth pressure. It is the pressure that at all times are tending to move or overturn the retaining wall. Next one is passive earth pressure. It is a reactionary pressure that will react in the form of a resistance to movement of the wall. Next one, active earth pressure. It is composed of earth wedge being returned together with any hydrostatic pressure caused by the presence of groundwater. This pressure can be reduced by the use of subsoil drainage behind a wall, inserting drainage opening called weep holes through the thickness of the stem to enable the water to drain away. Earth pressure behind a retaining wall is generally calculated by Rankine's theory for homogeneous incompressible questionless soil, assuming a hydrostatic pressure distribution along the depth. This is the calculation for calculating an active earth pressure. P equal to Ca gamma H, and P is the active earth pressure, C is the coefficient of active earth pressure. Ca can be calculated by cos delta into cos delta minus root of cos square delta minus cos square phi divided by cos delta plus cos square into cos square root of cos square delta minus cos square phi. Here gamma is the density of the retained material, H is the depth of the section below the earth, and delta is the angle of surcharge, and phi is the angle of repose of the soil. This is the figure. If there is no surcharge, that is delta equal to 0, the pressure P act parallel to the top surface of the material retained. The coefficient of active earth pressure become C equal to 1 minus sin phi divided by 1 plus sin phi. The total force behind the wall is given by area of the pressure triangle, and that is Pa equal to half Ca gamma H square per unit length of the wall, and acts at a depth of 2 by 3 h below the top. Ph is equal to Pa cos delta and Pv equal to Pa sin delta. Next one, passive earth pressure. This pressure build up in front of the toe to resist the movement of the wall. If it tries to move forward, this pressure can be increased by enlarging the depth of the toe or by forming a rip on the underside of the base. Rankine's equation for passive pressure is given as P equal to half Cp gamma H square. Here Cp is the coefficient of passive earth pressure, and it can be calculated by cos delta into cos delta plus root of cos square delta minus cos square phi divided by cos delta minus root of cos square delta minus cos square phi. Next one important point is for passive earth pressure and active earth pressure consideration. The passive earth pressure, it contain more in error, is quite high as compared with the active earth pressure. Its contribution in the design of retaining wall is neglected, which is on the conservative side. Retaining walls are seldom designed to retain a saturated fill, hence proper drainage must be ensured. Many times vehicles may travel over the retained material near the wall and cause the dynamic static pressure. The IRC and IR bridge rules prescribe an equivalent static surcharge for road and railway vehicles. Equivalent static static surcharge is also added in case of building is constructed near the top of the retaining wall. Next one, stability requirements. The designed retaining wall must be able to ensure the following. As per IS 456-2000, overturn does not occur and sliding does not occur. The soil on which the wall rests mustn't be overloaded, that is, the base width must be adequate to distribute the load to the foundation soil without exceeding its bearing capacity. Next one, check against overturning. As per clause 20.1 of IS 456 requires that the resisting moment is not less than the sum of 1.2 times the maximum overturning moment due to characteristic dead load and 1.4 times the maximum overturning moment due to the characteristic imposed loads. If the dead load provides the restoring moment, only 0.9 times the characteristic dead load should be considered. It further requires the restoring moment due to imposed loads should not be considered. The factor of safety against overturning may be computed by neglecting the contribution of vertical components of the active earth pressure if W is the sum of vertical load made up of weight of backfill on the inner slab plus weight of the wall and base slab plus weight of the front fill. If used, the factor of safety is given as follows. Factor of safety is equal to resisting moment divided by overturning moment, and that is 1 equal to 0.9 Wx1 divided by 1.4 pH into h by 3 and 1.5 equal to Wx1 divided by pH into h by 3. Where x1 is the center of gravity of the vertical loads from 2 and h is depth of the bottom of base below the earth surface and pH is the horizontal component of the earth pressure. Next, check against sliding. Sufficient frictional resistance must be available against sliding caused by the horizontal component of the earth pressure. Factor of safety equal to resisting force divided by sliding force, and that 1.4 equal to 0.9 mu W divided by pH and 1.55 mu W divided by pH. This is coefficient of friction, that is mu can be mu. The values are given. Soil, if the soil is coarse grained soil, mu is 0.55, and coarse grained soil with the silt, that is 0.45, and silt it is 0.35, and sound rock or rough surface it is 0.60. Next one, shear case. The sliding resistance of retaining wall is derived from the base friction between the wall base and the foundation soil. To increase the sliding resistance of retaining wall, other than providing a large surface weight and a large retained soil mass, shear case are to be installed at the wall base. The principle of shear case is as follows. The main purpose of installation of shear case is to increase the extra passive resistance developed by the height of the shear case. However, active pressure developed by shear case also increases simultaneously. The success of shear case lies in fact that the increase of passive pressure exceeds the increase in active pressure, resulting in a net improving of sliding resistance. In case of wall is unsafe against sliding, Pp equal to P tan square 45 plus 5 by 2, that is Pkp, and Pp is the unit passive pressure on soil above the shearing plane AP. P is the earth pressure at BC and at a boundary condition BC, and R is the total passive earth pressure that can be calculated by Pp into A. Next one, design of shear key. If sigma W, that is total vertical force acting at the key base, and phi is the shearing angle of passive resistance, and R is the total passive force, that is Pp into A, and P is the active horizontal pressure at the key base, and mu sigma W is the total frictional force under the flat base. For equilibrium, R mu sigma W equal to F of factor of safety into Pa. Therefore factor of safety is equal to R mu sigma W divided by Pa, that should be greater than or equal to 1.55. This is the figure of maximum pressure at the top. Let the resultant R due to sigma W and PA lies at the distance x from the toe, and x is equal to sigma m into sigma W. Here the sigma m is the sum of all moment about the toe. Then eccentricity of load E equal to B by 2 minus x, that should be less than B by 6. Minimum pressure at hill P minimum equal to sigma W divided by B into 1 minus 6E by B should be greater than 0. For 0 pressure E equal to B and B by 6, and resultant should cut the base within the middle third. Maximum pressure at the top P max equal to sigma W divided by B into 1 plus 6E by B should be less than safe bearing capacity of soil. Next one, depth of foundation. From Rankine's formula, depth of foundation df equal to SBC divided by gamma into 1 minus sin phi divided by 1 plus sin phi the whole square. SBC equal to, therefore df equal to SBC divided by gamma equal to k into Ka square, that is the coefficient of active earth pressure. This is the figure of depth of foundation. Next one, preliminary proportioning. It is T-shaped wall. Stem top width will be 200 mm to 400 mm, and base slab width will be, the B will be 0.4 h to 0.6 h and 0.75 h for surcharged wall. Base slab thickness equal to h by 10 to h by 14, and top projection equal to 1 by 3 to 1 by 4 of the base width. Next one, structural behavior of retaining wall. This is the deformation of the underloading of figure. Next one, stem design. Stem design for mu equal to Ka gamma h cube divided by 6, and determining the depth of D from mu equal to mu limit equal to QBD square. Designed as balanced section or under reinforced and fine steel. Mu equal to 0.87 and sigma Ck AST into D minus sigma Y AST divided by sigma CKB. The next step is check for shear at the junction and provide enough development length and provide distribution steel. Next one, curtailment of bars. This is the curtailment of bars figure. Next one, analysis of counterfort retaining wall. When H exceeds about 6 meters, stem and heel thickness is more. When more bending is acting at the stem base, more steel will be required. Hence, cantilever T-type retaining wall is uneconomical. Next, counterforts. Their trapezoidal section is provided at a spacing of 1.5 meter to 3 meters center to center. Next one, parts of a counterfort retaining wall. It is counterfort retaining wall is same as cantilever retaining wall. The additional one is counterfort. This is the plan and cross section of the counterfort. It contains stem, toe, heel, and base slab. Additional one is counterfort. Next one, design of stem of counterfort retaining wall. The stem acts as a continuous slab. Soil pressure act as load on the slab. If the pressure varies linearly over height, the slab deflects away from the earth face between the counterforts. The bending moment in the stem is maximum at the base and reduces towards the top, but the thickness of the wall is kept constant and only the area of the steel is reduced. Maximum bending moment for stem. Maximum positive bending moment equal to PL square by 16, it occurring midway between counterforts. The maximum negative bending moment that will be PL square divided by 12, and it is occurring at the inner face of counterforts, where L is the clear distance between the counterforts and P is the intensity of soil pressure. This is the figure of maximum bending moment for stem. Next one is design of toe slab. The base width B equal to 0.6 h to 0.7 h. The projection equal to 1 by 3 to 1 by 4 of the base width. The toe slab is subjected to an upward soil reaction and is designed as cantilever slab fixed at the front surface of the stem. Reinforcement is provided on at the face along the length of the toe slab. In case of top slab's projection is slabs that is greater than B by 3. Front counterfort are provided above the toe slab, and the slab is designed as continuous horizontal slab spanning between the front counterforts. Next one is design of heel slab. The heel slab is designed as a continuous slab spanning over the counterforts and is subjected to downward forces due to weight of soil plus self weight of the slab, and an upward forces due to the Soil reaction. Maximum positive bending moment is equal to PL square divided by 16. It is occur on the midway between counterforts, and next one is maximum negative bending moment, that will be equal to PL square divided by 12, and it is occurring at the counterforts. Next one, design of counterforts. The counterforts are subjected to outward reaction from the stem. This produces tension along the outer sloping face of the counterforts. In the inner face supporting the stem is in compression. Thus, counterforts are designed as a T-beam of varying depth. The main steel provided along the sloping face shall be anchored properly at the both ends. The depth of the counterforts is measured perpendicular to the sloping side. This is the behavior of the counterfort of retaining wall. The important points considered will be load on the wall, deflector shape, nature of the bending moments, position of the steel, and counterfort details. Thank you.